In this video, it's my goal to integrate this function 3 times. The first time I integrate, I actually am just going to use a substitution. The next time I integrate, in the next way, I'm going to do an integration by parts. And then finally, I'm going to establish this using a trig substitution. And my actual goal is to think about which way I'd actually usually approach this problem if I just kind of met it in the wild. I have all of these options. I've learned all of these integration techniques. So let's start by doing a substitution, and then we'll visit the other ways through the problem. So here I'm supposed to, or I want to, use a substitution. So I'm going to say let u equal x squared plus 1. So du equals 2x dx, and I'm ready to make my substitution. And in this moment, I have some algebra to do to simplify it. Everything's going pretty well. I'm write that 1/2 out front. And I have this x squared in it, but I look up here and, well, if x squared plus 1 is u, that means u minus 1 is x squared. Still have that 1/2 out front to worry about, but I can distribute. And I'm ready to take an antiderivative. So I end up with a 1/5 u to the 5/2 minus a 1/3 u to the 3/2 plus c. Let's fix the denominator of that fraction. I remember what u was. U is x squared plus 1. And so there's my first pathway through the problem, just doing a regular old substitution. And I get this 1/5 times x squared plus 1 to the 5/2 minus 1/3 x squared plus 1 to the 3/2 plus some arbitrary constant. Well, next up, I want to approach it as an integration by parts problem. And I have to be at least a little clever to get this into a format where I have a function that's easy to differentiate and one that is easy to integrate. Of course, the word easy in there might be in quotes. I'm going to let u equal x squared, and I'm going to let dv be x root x squared plus 1 dx. Du easy to calculate. I might need to work a little harder to find v here. So I look at this and I think this is a substitution problem. Well, let's let u equal x squared plus 1. This feels familiar from the last way I worked this problem. So it's like even if I did an integration by parts, it's like hiding a little bit of a substitution problem anyway. So let's see, I'd have a u to the 1/2. I have this x out here, and I have a du over 2x. So the x's definitely cancel, and I could imagine that 1/2 out front. So I end up with a u to the 3/2 times that 2/3 plus c. It's in this moment I realize I'm really overusing the variable u in this problem. I got u's everywhere, but I think we can interpret everything. I get that x squared plus 1. All right, so that is actually my value for v, 1/3 x squared plus 1 to the 3/2. I'm not going to write down the plus c because I don't need it there. Any v will do. So that was kind of scratch work just to get to that point. But now let's see what happens as I follow the integration by parts formula. U times v, so x squared, and then times that 1/3 x squared plus 1 to the 3/2, minus the integral of v du. See, I end up with a 2/3 I can write out front, and then an x times an x squared plus 1 to the 3/2 dx. And now I need to integrate this part, and that's another substitution problem. And at this point, I think I've already decided I like the other method better. All right, I like the substitution path through this problem a little bit better, but it's always good to get practice doing different things. So I'm going to continue working on this problem just here using a substitution, which means I'm not really ready for those brackets yet. And I'm going to cheat a little bit. This is a substitution I want to make. I want to let u equal x squared plus 1, and since it's already sitting over there, I'm just going to say that's a u to the 3/2, and du over 2x. The x's cancel, and the 2 can actually cancel with that one hanging out there. So let's see what happens. I end up with an x squared over 3 times x squared plus 1 to the 3/2 minus 1/3. And let's see what happens here. U to the 5/2 times that 2/5, and then plus c. I'm going to try to sneak in my antiderivative here. X squared over 3 times x squared plus 1 to the 3 over 2 minus 2/15. U was x squared plus 1 to the 5 over 2 plus c. And there might be those amongst you watching this video saying, oh no, that's a different answer. And what I would say is it's a different looking answer, because it turns out these are actually equivalent solutions. Remember, antiderivative formulas can look different and still be the same. In fact, they can differ by the constant. Now, it turns out these two algebraic expressions we've seen so far are actually equal. In the YouTube description, I've linked a Geogebra page that shows they're equal. And if you're watching this as part of our coursework at Alamance Community College, you can find that link to our Moodle page as well. All right, but we found an antiderivative formula by integrating by parts. We have found one by doing a substitution. And the final way I wanted to go through this problem was to do a trigonometric substitution, which is really what we were studying this week. And I see an x squared plus 1. So I'm thinking that this is an x equals tangent theta substitution. We need to take a derivative, and the derivative of tangent is secant squared. I'm ready to perform our substitution. I end up with a tangent cubed theta times the square root of tangent squared plus 1, which of course is secant squared theta, times another secant squared theta. So let's see what happens here. I end up with a tangent cubed theta. That's secant times secant squared. That's secant cubed theta d theta. Well, what I chose to do next when I worked this one out was to rewrite everything in terms of sine and cosine. This would be a sine cubed over a cosine cubed. This one's a 1 over cosine cubed, so this is really a 1 over cosine to the 6th theta on the bottom. Excuse me, well, yeah, 1 over, but a sine cubed over a cosine to the 6th is what we really end up with. And so I'm going to approach this problem like one of the trigonometric integrals we saw earlier. By splitting off one of the sines. On top I have a 1 minus cosine squared theta. And here I'm ready to perform a regular substitution. Don't know why I'm calling them regular through these videos. It's just substitution, but we have all these other things now, and something amuses me by calling them regular. I guess that's as opposed to being a decaf substitution. All right, and again, I end up with that minus du here. I'm going to go on and change the order of the arithmetic here. U squared minus 1 over u to the 6th, integrating with respect to u. I'm going to do this division, so that'll be my first step on this next board. U to the 2nd divided by u to the 6th would be a u to the minus 4th minus a u to the minus 6th. Integrating with respect to u. Oh, I think I'm ready to go on and anti-differentiate. U to the minus 3 divided by that minus 3 minus a u to the minus 5th divided by that minus 5 plus c. And I just need to remember what u was. U was cosine. Oh, write that down the same way. Left off my cube there on the bottom. I should get that in there. And now I need to remember that wasn't even my original variable, right? That's what u was. And now I need to remember that my original variable was x. And I'm working with an x equals tangent theta. We can imagine the right triangle that comes from. Tangent is the opposite over the adjacent, making the hypotenuse the square root of x squared plus 1. A cosine in this triangle would be a 1 over root x squared plus 1. Minus 1 over 3. That cosine's on the bottom, so I can just imagine taking a reciprocal. And there's a nice, happy antiderivative formula. And so we have now done this one 3 different ways. And these two, the substitution, the trigonometric substitution, actually give us exactly the same answer. Those are really 1/2 exponents, so I could change the order around and get that same answer written there. And then we got a subtly different answer. Not subtly, a fairly different looking answer when we did the integration by parts, but an equivalent antiderivative formula. That's it for now.